This is slide number 71 and I am your presenter Asloob Mudassar. Holography. Holography, you know, that provides you a mean of recording the amplitude image. And in the Fourier optics, in the previous slides, we have been talking about either the recording of intensity images or the amplitude images. So by using holography, you will be able to record the amplitude images. Holography, a process of recording three-dimensional objects or scenes. In technical words, wavefronts generated by a scene are recorded, and then later on the same wavefronts are reconstructed, giving 3D information of the object. Holography may thus be regarded as construction and reconstruction of wavefronts. High-resolution photographic films or photographic plates, which we may call photoglass, are required to record wavefronts. These photosensitive materials respond only to the intensity of light incident on them. The storage of wavefronts is done in the presence of another beam called reference beam, and the wavefronts generated of an object form a beam known as the object beam. The reference beam is directly incident on the photosensitive material in the presence of the object beam. The reference beam and the beam incident on the object must be generated from the same coherent source, usually a laser with high spatial coherence. The spatial coherence of the laser must produce very high contrast fringes at the photosensitive material. The recorded interference pattern is regarded as the object interferogram. So you see that in holography we shall be recording the object interferogram, that is the interference between the reference beam and the object beam. The wavefront which is reflected or scattered off the object beam, that is called the object beam, and the reference beam is a beam which is directly illuminates the photosensitive material. So these two beams at the photographic plate interfere with each other, forming an interferogram called object interferogram, and this object interferogram is recorded in holography. The exposed photosensitive material is developed and fixed, which is then referred to as the hologram of the object. To reconstruct the original wavefronts, the hologram is illuminated with a beam identical to that of the reference beam used in the recording process. The illuminating beam undergoes diffraction at the hologram and produces wavefronts identical to those stored in the recording process. There exist a large number of different types of holograms with the different applications, but all have one thing common, that is the recording and the reconstruction of wavefronts. Here we want to see how Fourier optics can help us in writing the necessary mathematics used in the construction of wavefronts and in the reconstruction of wavefronts in different types of holograms. Wavefront recording and retrieval. When an object is illuminated with a spatially coherent beam, a wavefront is reflected or scattered or diffracted off the object depending on the nature of the object. The wavefront from the object contains full information about the amplitude and phase distribution at the object plane. When such a wavefront reaches at the intensity detectors, for example photographic plates, photoglass or CCD cameras, the phase information is lost and the amplitude is converted to intensity. Special arrangements based on hologram reconstruction, special arrangements based on hologram construction are made to record both the amplitude and phase information, and special arrangements based on hologram construction are made to retrieve both the amplitude and phase information of the object. So you see that if you want to retrieve the data stored in the hologram, that is, you want to obtain the phase, amplitude and phase information of the hologram, you need to follow some techniques which we call hologram reconstruction techniques. A beam from a coherent source with high spatial coherence, for example gas-based lasers or particular helium laser, etc., is split into two parts. One part of the beam is directed towards the object, and the returned signal is referred to as the object beam. The second part of the beam is directed onto the photosensitive material, for example, photographic plate, or onto the photoglass, etc., and is referred to as the reference beam. The two beams, or more accurately, the two wavefronts, that is the object wavefront, the reference wavefront, interfere at the photographic plate, and the resulting interferogram or a hologram is recorded. The setup to record the hologram of a solid diffuse object is shown in the figure below. For example, this one. Caption: object wavefront, that is the hologram recording setup. We have a laser source, maybe for example helium laser source. The beam is expanded because the diameter of the original beam is very small, so we need to expand the beam using the beam expander. Now the beam has expanded. Now there is an object which is being illuminated by the beam directly, and also there is a beam splitter we have placed in between the object and the laser source. Now you see that the beam splitter is tilted in such a way that the beam incident from the laser source is reflected towards the photoglass from the beam splitter. And you know that we have shown the wavefront in the solid line. These are the wavefronts reflected from the beam splitter, and these solid wavefronts are actually the reference wavefronts. So the beam which illuminates the object is scattered off the beam in all directions, and a part of that scattered beam is received by the photoglass. So the scattered beams have been shown with light intensity. So you see that the scattered or the object wavefronts have been shown, and in the solid the reference wavefronts have been shown. These two wavefronts reach at the photographic plate or the photoglass, and they interfere together, forming an interference pattern which we call the object interferogram. So this is the basic construction method or the procedure by which we can construct the hologram. To give a mathematical representation of the hologram recording process, we define the object beam O as a function of xy, and the reference beam R as a function of xy. Xy actually as a point is a point on the photosensitive medium in the following form. So we have the object beam and we have the reference beam. We have written the contribution of object beam and the reference beam at the point x and y, and the x and y is the point on the photographic film we are considering. So the object beam can be written as the amplitude of the object multiplied by its phase factor, which is e to the power minus eta phi naught at the point xy. And similarly for the reference beam, we can write r of xy is equal to magnitude of r multiplied by the phase factor, which is e to the power minus iota phi r at the location x comma y. So we have equation 1 and 2. Equation 1 is the object beam, and equation 2 is the reference beam. These two beams reach at the photographic plate, and they interfere together and form an interferogram, where phi naught of xy contained in equation number 1 and phi r of xy contained in equation number 2 are the values of the phases due to the object and the reference beams respectively at the point of the interferographic plate. The intensity of the resulting interferogram and the interference pattern can be written as. So we are now, you see that we have these, the object beam from equation 1, the reference beam from equation number 2. Now these two will interfere and form an intensity pattern at the photographic plate. So we are going to write down the intensity, the mathematics for the intensity expression, which is given in equation number 3. So I of xy, that is the intensity at the point xy on the photographic plate, is equal to absolute square of object beam plus a reference beam. So you see that we are writing the coherent addition, and we are writing the coherent intensity I. So we have the two amplitudes, that is the O, the object O in the form of amplitude, the reference beam R in the form of amplitude. We are adding together and we are taking the absolute square of that quantity, and then we are expanding. You see that we have in the first bracket on the first row we have the amplitude, we have O plus R, and then we have the complex conjugate of O and R. So this star indicates the complex conjugate, but you know that in the rest of the discussion we shall just be talking about the word star, not talking about the complex conjugate again and again. So this star would mean complex conjugate of these quantities. So you see that in the step 2 we have expanded, we have multiplied these two brackets, and then we have obtained the 4 terms in that bracket. So you see that in the last step of equation number 3 we have the absolute square of O plus O multiplied by R star plus R multiplied by O star and plus R mod square. So we have O mod square on the left hand side, we have R mod square on the rightmost side of equation number 3, and then we have other 2 terms which are the O into R star plus R into O star. So these are the 4 terms that would appear in the intensity expression. So use of equation 1 and equation 2 in equation number 3 lead to the following equation. So you see that here we have kept, here we are in equation number 3, we are using the left hand sides of equation number 1 and equation number 2. Now we are substituting their values from the right hand side. So using the right hand side expressions from equation number 1 and 2, we can write the intensity expressions as given. So you see that at the last step we have converted all the terms into the intensity, and those those which were in the amplitude form, but we have taken the mod values of those one, that is in step 2, that is the mod of O and the mod of R. We have converted them into the intensity, that is I naught and IR, but we have taken the square root of that one. So we have represented the intensity of the object beam, that is the O mod square, by I naught, and the intensity of the reference beam, that is the R mod square, by IR. R subscript stands for the reference intensity. And then you know that the rest of the 2 terms have also been combined, and we have the cos of phi naught minus phi R. So this is the cos term that would produce the fringes at the interferogram. So if you look at equation number 4, we have I naught, which is a constant at the point x, y. IR is also a constant term because these are the constant contributions, but you know that the last term, that is the cos of phi naught minus phi R, will produce some values which depends on the relative phase difference between the phase of the object beam and the phase of the reference beam. So this could be different depending upon the phase values. The minimum value of cos, you know that is equal to -1, and the maximum value of cos is equal to +1. So between these values it will change. So it means that depending upon the value of cos, the term in the square root, the sign with the term in the positive sign we have shown with the square root of the term, that could change, that could be minus, that could be plus, and that could take any value depending upon the value of the cos of phi naught minus phi R. So cos of phi naught minus phi R will range from -1 to +1. So that range of values will be applicable in equation number 4. So here I naught is equal to O mod square and IR is equal to R mod square are respectively the intensities at the point on the recording plane due to the object beam and due to the reference beams acting alone. The relative phase difference between the object and the reference beam, that is phi naught minus phi R, appears as an arrangement of the cosine function. The cosine term cos of phi naught minus phi R thus encodes the phase of the object wavefront in relative terms, that is in terms of intensity. So you see that here the phase of the 2 objects through the cosine function has been coded in the form of the intensity in equation number 4. For accurate recording of the intensity, that is I of xy, recording must be done in the linear region of the TA, that is the amplitude transmittance versus the exposure curve of the photographic medium. Typically TA versus the E curve is shown in the figure. So you can see that in this curve we have plotted the exposure on the horizontal direction on the along the horizontal axis, and we have plotted the amplitude transmittance of the photographic plate on the vertical axis. So you see that the amplitude transmittance has a maximum value of 1, and of course the minimum value is 0. So you see that with the exposure, the amplitude transmittance will change according to the value of the exposure. If the exposure is very high, then you know that the photographic plate will be totally black due to the high exposure, and no light will pass through that one. So if the exposure is almost 0, it means that we have not shined the photographic plate with any light, which means that the plate has no exposure, which means that when developed, the plate will be transparent. But you know that if we have some reasonable value of the exposure, then of course, for example, according to the value of 0.5 at that amplitude transmittance, it means that some light can be stopped and some of the light can be passed through. When that it means that this is a linear region. So in this linear region, there is a linear relationship between the amplitude transmittance and the exposure. And this region is the required region where we want that overexposure should occur in this region. So we should control the exposure depending upon the intensity of the object beam, the reference beam. We should depending upon their total intensity, or depending upon the total intensity given by equation number 4 on the left hand side, that is I of x comma y. So depending upon the value of capital I, this capital I of xy should fall in this region, in the linear region. So we should decide the time in such a way that I should fall in this region. So if I is falling on the left side of this linear region, we can increase the time so that we can have I in this linear region. And if I is on the right side of this linear region, we should reduce the exposure time so that we can again fall in the linear region. So the recording must be done in the linear region, because it is a region where there is a linearity between the exposure time and the amplitude transmittance of the photographic film. The developed photographic plate, which we regard as the hologram of the object, must have its amplitude transmittance recorded in the linear region. Moreover, the MTF, that is the modulation transfer function of the recording material, must have a significant value at the highest possible spatial frequency in the interferogram. The spatial frequency f as a function of xy will vary on the recording or the interference plane, and is defined by the following equation as given in equation number 5. So the spatial frequency of the fringes will be f as a function of xy, because the spatial frequency will vary on the hologram plate, on the holographic plate, or on the photosensitive material, is given by sine of theta as a function of xy divided by lambda. Lambda is the wavelength of the illuminating sources. So you see that over this frequency must fall in such a way that the photographic plate can record this value f. Because if the spatial frequency is very high, it might be possible that an ordinary film would not be able to record such a very high frequency. So we are using the photographic plates or the photoglass for the recording of the interference pattern in the hologram, so that we have these films with a very high MTF, so that we can record the spatial frequency, very high spatial frequency produced at the Fourier at the hologram plate or at the photographic plate given by equation number 5, so that we can record the very high spatial frequencies of the fringes using photographic plates of a very high MTF, where theta of xy is the angle at the point x comma y between the object beam and the reference beam. The photographic plates which are used for the holography purposes usually have very high values of MTF, much greater than the highest expected spatial frequency at the recording plane. Recording of interferograms on CCDs, that is on the charged coupled devices, is also possible, but with special care, because the CCDs have very much smaller MTFs than the required MTFs. Of the CCDs are usually much lower than the photographic plates used in the holography. So the MTF of the CCD cameras are usually much smaller than or much lower than the MTF required for the MTF of the photographic plates used in holography. A smaller value of angle between the object beam and the reference beam will lower the value of the highest spatial frequency at the recording plane, making the use of the high quality CCD possible in the recording of the interferograms. So you see that in equation number 5, if the value of theta is the angle between the object beam and the reference beam, if the reference beam is aligned in such a way that theta is very small or close to 0, then of course what will happen, f will be very small, and when f is very small, then of course very high quality CCD camera can be used to record the interferogram. But if theta is large, which means that the f is large, then you know that an ordinary or even a specialized CCD camera would not be able to record the interferogram fringes, because for that one we need special photographic films which have a very high value of MTF to record such interferograms. Use of small value of the angle poses a problem in the reconstruction process where the beams generated by the holograms can overlap. So you see that if theta is very small, we can record the hologram, but when we shall use the hologram to reconstruct the object beam and the reference beam, that is the reconstruction of the hologram, then you know that in that process we would not be able to separate out our required beams from the reference and the object beam, and then of course there will be an overlapping between the 4 terms. You see that we have shown 4 terms over here, or approximately the 3 terms in equation number 4. So there will be an overlapping between these terms, and we would not be able. You see that in equation number 3 there were 4 terms. So these 4 terms will then overlap with each other in the reconstruction process if the angle is small, and we would not be able to separate out the term 1, which was O mod square, and the term last term, which are R mod square. These 2 terms will coincide with each other, but the other 2 terms which contains R star and the other term which contains O star, they will be separated out from the other 2 terms, and you see that we need to extract the term R star and the term O star so that we can reconstruct the hologram. And if the angle is small, then of course all these 4 terms will merge together and we would not be able to separate them out. So that's why we need to use a significant value of the angle theta from equation number 5, so that all the 4 terms are all the 3 terms in equation number 3, because R mod square and O mod square will be in the same direction, and so the other 2 terms will be in opposite direction. So there are 3 possible directions, so all the 3 terms should be well separated. So we need to use a significant value of the theta. We shall discuss in detail what should be the value of theta in this case, in this particular case. The amplitude transmittance, we are now writing as 2A, because we have already used T previously. Now we are using T2A. So T stands for the amplitude, T stands for the transmittance, A stands for the amplitude, and 2 stands for the, because we are here talking about the amplitude transmittance of the hologram. So the amplitude transmittance T2A as a function of xy of the developed holographic plate, which we call hologram, may be written as given below. So you see that the amplitude transmittance of the hologram is proportional to that we have proportional to that of the equation number 3, the terms in equation number 3. And the only difference is that we have shown over TB. TB is actually the term that stands for the uniform bias term. So this is a uniform bias term. I shall be explaining that one also. And then we have a plus beta times, and within that we have the 3 terms over here. One is the O mod square term, and the other 3 terms, one is O or R star plus R O star as given in equation number 6. Where is the R mod square term? R mod square term is actually the TB term. So that what we have separated out the reference term in the form of TB, and then we have the object beam square, we have O mod square term, and then we have the other 2 terms multiplied by beta prime as given in equation number 6, where TB stands for a uniform bias due to the reference beam and is due to the uniform reference wave contribution at the recording plane. If reference wave is a collimated beam, then TB is perfectly a constant, and if it is a spherically diverging wave, then it is approximately constant. The constant beta prime is defined in the following way. Beta prime is equal to the slope of TA versus E curve at the bias point multiplied by exposure time. And you know that this slope of TA versus E curve at the bias point is represented by beta on the right hand side, and the exposure time is represented by TEXP, stand for exposure, as given in equation number 7. So this is the value of beta prime. Now if we have chosen these parameters in such way that if beta prime is less than 0, beta prime will be less than 0 for negative transparency, and beta prime is greater than 0 for positive transparency. To reconstruct the object wave, the developed photographic plate, which we call hologram, is illuminated by a wave identical to the reference wave used in the recording process. Let's represent the reconstruction wave by R prime. So you see that now our hologram has been constructed, and now we want to reconstruct the hologram. That we can obtain, that we want to obtain the recorded reference wave front and the recorded object wave front. For that one we need to illuminate the object with a reconstructing wave, which we are referring over here as R prime. X, y. So R prime can be represented as the mod of R prime multiplied by the phase factor, which is e to the power minus iota phi of xy. You know that before that we have used two values of phi naught for the object phase and phi r for the reference phase, and here we are using just generally phi as a function of xy. So this R prime is our reconstructing wave, and the reconstructing wave will be multiplied by to the amplitude transmittance of the hologram. So equation number 6 gives you the amplitude transmittance of the hologram, and we shall be multiplying the reference. We shall be multiplying the R prime beam to both sides of this equation number 6, which we have done in equation number 8. So R prime on the left hand side has been multiplied with the amplitude transmission of the hologram, that is T2A as a function of xy, and on the right hand side you know that we have all the terms from equation number 6. So these are actually the 4 terms, TB term and the other 3 terms contained within beta prime. So we have multiplied R prime. You see that R prime has been multiplied to all the terms. So here generally we have multiplied R prime, in the second step we have multiplied R prime to TB, and then we have multiplied R prime to beta prime term, which contains in the parentheses 3 terms. And then you know that in the last step we have represented the equation without showing the coordinates x and y, because we now assume that it is a contribution at a general point xy through the hologram. So we have the last step of equation number 8 can be read as R prime multiplied by TB plus beta prime R prime and multiplied by O mod square, and the third term is beta prime R prime O into R star, which is R star means R conjugate, and then beta prime R prime O R and O star, which means or conjugate. So you see that the 2 terms which will be very of significant importance to us is the third term which contains R star, and the 4 terms which contains O star. So these are the terms that we can construct our object beam and the reference beam from these 2 terms, which we shall see later. The first and the second term, as we have shown in equation number 8, the first and the second term which we have combined in the parentheses over here are the undifracted wave and travel in the direction of R prime. So the beam that we illuminate the object, these 2 terms will travel in the direction of the R prime, that is the reconstructing wavefront. That is the reconstructing reference wave, or that is the reconstructing wave which is identical to the reference wave, which is R prime. The third term, which is beta prime, R prime O and R star, can be used to reconstruct the exact object wave O. So you see that this term, third term, contains object O. So it means that we can reconstruct the object wavefront using the third term if the reconstructing wave is identical to the reference wave, which we shall see. If over r prime is equal to r, then you know that here in the third term you have r multiplied by r star will give you r mod square, and then you know that we can construct O from here. That is, look at this one. So we have, let's set r prime is equal to r. Then you know that the third term, in the third term we have a beta prime, r prime, O and r star, and then on the right hand side we have replaced r prime by r, and then you know that we have r and r star, which means that r is multiplied by with its complex conjugate, so we have r mod square, and then we have a beta prime, r mod square and O. This O is actually the object beam that will be reconstructed, because r mod square will be a constant contribution and beta prime is also a constant. So O, which is object beam, can be recovered when the reference, when the reconstructing wave r prime is equal to the exactly equal to the reference beam that we have used in the construction process. Now reconstruction of the object wave O using an identical reference wave r is shown in the figure. For example, this figure, we shall be discussing this figure. Let's read the first paragraph. The fourth term, which is beta prime, r and O star. So you see that here we have r term as such present. Originally r is present, which gives you the reference beam, the original reference beam, and then we have O star, which is the complex conjugate of O. Can be used to reconstruct the conjugate of the object wavefront, that is O star. So here we can construct, from the fourth term we can construct the O star, and you know that in the third term O was present and we could construct O from here. But you know that from the fourth term we can construct the O star, that is the complex, that is the conjugate of the object wavefront. If the reconstructing wave is equal to the conjugate of the reference wave, that is r star is equal to, that is r prime is equal to r star. And then you know that if you set r star is equal to, if you set r prime is equal to r star, that is the, if you are setting the reconstructing wave is equal to the complex conjugate of the reference beam that you have used in the reconstruction of the hologram, then you know that you have to place this value over there, that is beta prime r into O star will be equal to beta prime r star into r into O star. So r star and r will be replaced by r mod square. So you have a beta prime, then r mod square multiplied by O star. So r mod square is actually constant, beta prime is also constant. So O star, you know that will be reconstructed. The reconstruction of the conjugate wave O star using a conjugate reference wave r star is shown on the next figure. So let's first of all discuss the reconstruction of the object O as shown in this setup. So let me read setup for the reconstruction of the object wavefront from the object hologram. So what we have done is that we have placed the hologram over it. So this is the hologram, you know, object hologram. So it has been placed originally in the same setup where it was used for in the recording process. So let me show the recording setup. This is the recording setup. So we are using the same recording setup where the hologram was, where the recording film was played, where the hologram was recorded. So this is the recording setup. Now you see that on that recording setup we have replaced the photographic film or the photo glass by the object hologram. So now this is the hologram, not the photographic film but the hologram. So this is the hologram, and you see that we have the laser source which illuminates the same setup as before, that is the beam splitter is there, the object beam is there, the object is there, but you know that we have placed a beam splitter so that the beam from the laser source should not reach the object. So the object beam has, so there is no illumination of the object, because we have placed a beam splitter in the path of the object beam and the reference beam. Now the beam splitter is originally there. The light from the beam splitter, you know that the wavefronts have also been originally shown, which are the wavefronts corresponding to the reference wavefront. So these wavefronts are reflected of the beam splitter will illuminate the hologram. So when the hologram is illuminated with the reference beam, then you know that one beam which goes straight in the same as the reference wave, these reference wave will go straight undifracted. As we have shown that in the solid lines, solid curve lines are actually the reference wavefront which are going straight through the hologram. And then you know that these there are other reconstructed object wavefronts which we have shown with the diffuse or with the diffuse light, and you know that these are the reconstructed hologram. It appears that these reconstructed object wavefronts are coming from the object as if the object is originally placed over there. So if you look from the, if you place your eye in the path of the reconstructed object wavefront, you would see that if the object is originally present at its original position and is being illuminated with the laser. But you know that here we are reconstructing the object, that is the object beam has been stopped, but we are using the hologram to reconstruct the original wavefront. So we have here constructed the object wavefront. It means that if you place your eye in the path of the object wave and then look through the hologram, then you see that you would be able to see the object as if the original object is placed. But you know that there is a beam stopper on the path, you cannot see the original object, but these reconstructed object wavefronts would provide you a means to perceive as if the object is originally placed. Okay. So you see that you have two wavefronts. One wavefront is the reference wave which is going undifracted through the hologram, and then of course giving birth to the reconstructed object wavefronts. And you know that the virtual image of the object will be constructed because the object will appear behind the hologram. So if you place your eyes in the path of the reconstructed object wavefront, and if you look through the hologram, the object will appear behind the hologram. It means that this is the virtual image of the object. Now you see that if you extend these wavefront, that is the reference wavefront, backward, you will see that it will appear that if these wavefronts, that is the wavefronts, are coming from the virtual point source, which we have extended backward by joining the actual propagation directions of the reference wave have been extended backward to find out the location of the virtual point source. So the real point source is in front of the laser, and the virtual point source is at the back of the photograph, is at the back of the beam splitter. So actually this is a setup that we use in order to construct the object wavefront. So this will provide you the means to construct the wavefront, and the object that you will see will be virtual object. And this is due to the third term. So in the third term you have constructed this object. Now what about the fourth term? The setup, the fourth term would help you to construct the real image of the object. So let's see that how the real image can be constructed. This is the setup. Let me read the setup. Let me read the caption. Virtual setup for reconstruction of a conjugated object wavefronts. Not a virtual setup, but you see that it could be a real setup also. So setup, so ignore the word virtual. Setup for the reconstruction of a conjugated object wavefronts from the object hologram using a conjugated reference wavefront. So we are using here the conjugated reference wavefront. As you have seen in the fourth step, we are using R prime. We are using R prime is equal to R conjugate, that is R prime is equal to R star. That is for the fourth step, we are using R prime is equal to conjugated R beam, conjugated reference beam. So conjugated of the original reference beam which was used in the construction of the hologram. So we are using the conjugated reference beam to reconstruct the hologram in this case. for the fourth term. So this setup actually addresses the fourth term, reconstruction from the fourth term. You know that here we have shown the conjugated reference wavefront, which is the R star, or R prime is equal to R star. So these are the wavefronts which illuminate the object, and you know that these are the beams which are being focused on the hologram, and after the hologram they will travel straight and will focus somewhere at some real point source. So when these wavefronts, that is the conjugated reference wavefronts, will illuminate the object, then of course the conjugated object wavefronts will be produced. But you know that these wavefronts would not be the same as the wavefronts we have shown over here. But these, you know that if you see that these are actually diverging wavefronts we have shown. But you know that here we have shown the conjugated object wavefronts which are actually converging. Look at the shape of the wavefronts we have shown. The shape of these wavefronts and the shape of this wavefront. These wavefronts, that is the object wavefronts, are now converging wavefronts. So they will converge to form the real image of the object. So the real image will be formed in front of the object, whereas the virtual image in this case will be formed behind the hologram, and the real image will be formed in front of the hologram. Okay. So if the angle between the reference, let's discuss the angle. If the angle between the reference and the object wave during the recording process is small, then in the reconstruction process, the third term and the fourth terms will be partially overlapped by the first and the second terms. For even smaller angle, the third and the fourth term can also partially overlap. The partial overlapping will restrict full recovery of the object wavefront and its conjugated wave. So you see that we have these, you know, that four terms as appear from equation number 3. We want these four terms to be well separated from each other. The first the term, that is O mod square and R mod square, will be travel along the same direction, but the other two terms will be traveling in opposite directions. So it means that we need these two terms to be separated from each other and also from the central terms. So the one of the beam will be on the left of the first and the fourth term, and the other term will be on the other side of these two terms, that is the O mod square and R mod square term. So we want to avoid the overlapping, and the overlapping can only be avoided when use an appropriate value of the angle. So that's why we are discussing the angle over here. The third term, this one, are the diffracted wavefronts which further diverges as the wavefront propagate towards the right, or which appears to emanate from some points behind the hologram. The virtual image is thus located behind the hologram when viewed through the hologram from the right side of it. So this is what I have already explained. The wavefronts corresponding to the fourth term, this one, converge to a real image on the right hand side of the hologram. Figure on the right, not figure on the right, but this figure, you know, this is the figure I am talking about. And okay, so the figure. So this figure shows the diverging object waves on the right side of the hologram forming a virtual image, and converging wavefronts forming a real image are not shown. So this will form a converging wavefronts through the hologram, and we have not shown the real image over here. But you know that these converging conjugated wavefronts will form a real image of the object. The figure also shows a small overlap between the third term, this one, and the first and the second term over here. So you see that here we have shown a small overlap between the reference beam, outgoing reference beam forming a real image, and also the conjugated object beam. But you know that if you set the angle in such a way, then you can also separate out the conjugated object wavefront from the reference wavefront going towards the real image, and then of course there will be a separation between the two, and you can see the real image on the right hand side of the hologram. Let's discuss the third and the fourth term when the object consists of a single point source. So you see that here, rather than discussing the whole object, we are considering actually a single point source. You know that before that we have been considering the whole object as shown in this figure for when the object was, when the hologram was constructed. Now we are using this object as a single point source instead of that object. So let's discuss the third and the fourth terms. When the object consists of a single point source, the object will generate spherically diverging wavefronts at the recording plane. The object wave defined in equation 1 can be written in the following form. So we have the object which is equal to O naught, that is the amplitude of the object, or you can say that O naught is actually the mod value of the object O, and then you know that we have the phase term which is e to the power iota k, and then rather than using the phi we have the under root sign which contains x minus x naught square plus y minus y naught square plus z plus 0 minus z naught whole square. So this is equation number 9, and then we have written this the object. We have written the object for a single point source. So this is the and now the phase is in the form of the e to the power iota k into the this factor. You know that this factor is very important, and this actually arises why? Because x comma y comma 0 are the coordinates defined at the recording plane, and x naught, y naught, z naught are the coordinates where the point object source is located. So that's why we have recorded this value from that one, and you know that this is the square root of this quantity. So remember that. And this why this is coming, because we have explained that x comma y comma 0 is the point source at the recording plane, and x naught, y naught, and z naught are the coordinates where the object point is located. And you know that when x, y on the hologram on the photographic plate will change, because x comma y comma 0 is a general point on the hologram plate, because we have placed the hologram at a distance, for example at the location, and because we have placed the photosensitive material or the photographic plate at the location where z is equal to 0, and you know that x, y are the general points on the photographic plate. So x, y is any general point. So when these points will change, then of course the phase as according to equation number 9 will change, but x naught and y naught and z naught, which is the location of the point source, would not change for a single point source. The amplitude of the spherical wave is represented by O0. The third and the fourth term respectively take the following form. So under that condition we are writing the third term, which is equal to beta prime r mod square into O, and beta prime r mod square, and then we have replaced O by its value from equation number 9. So this is equation number 10. So this is the third term of the equation number 10. From the third term, it follows that when the hologram is illuminated with the same reference beam as used in the recording process, the object beam as a spherically diverging beam is produced. So you see that in the third beam we have written this third term when we are using the reference, when we are using a beam which is identical to the reference beam in order to illuminate that object. So here we had the term r multiplied by r star. That's why we have written r mod square. And you know that on the right hand side of equation number 10 tells you that it is a spherically diverging beam is produced traveling to the right direction from the hologram, making a virtual image of the point object at a distance z not behind the hologram, at the original location of the hologram. So the fourth term will be, for the fourth term we shall write object O e to the power minus iota k x minus x naught, and the rest of the things are the same, because here we are illuminating the object with the reference beam and you know that here we have O star, that is the conjugate of the object beam. So if we take the conjugate of object beam, we have a negative sign in the form of the exponent, that's e to the power minus iota k and the square root of the rest of the quantity. So this negative sign in the exponent is because we have O star over here. and the rest of the quantities are the same as we have explained earlier. So from the fourth term, it appears that when the same reference beam illuminates the hologram, a spherically converging beam is produced which focuses in front of the hologram, forming a real image at a distance z not in front of the hologram, because this is the focusing beam. So equation number 10 gives you a beam which is diverging. So due to this beam we shall see the virtual object behind the hologram, and equation number 11 gives you a beam which is converging beam after the hologram, and it will give you the real image in front of the hologram. So equation number 10 and 11 are applicable when the object consisting of a single point source was considered. In a real situation, a given object may be considered to consist of a large number of point sources with varying amplitudes and phases, and under such a condition, a superposition principle should be applied to the third term and the fourth term separately to obtain the resulting object beam and its conjugated versions respectively under illumination of the hologram by the same reference beam. Now we are going to discuss the constraint on minimum reference angle. In the reconstruction of object wave from a hologram, the hologram is illuminated with a beam identical to the reference beam used in the construction process. In the reconstruction process, it is required that the object wave and its conjugated version should not be overlapped by the undifracted waves through the hologram. And you know that there were two undifracted beams, as let me show through equation number 3. So you see that what are the undifracted beams? O mod square and the R mod square. These two are the undifracted beams from equation number 3. And the diffracted beams are the other two terms, one containing R star, the other containing O star. These are the diffracted beams. That is, they will move away from the undifracted beams in opposite directions. So it is required that the object wave and its conjugated version should not be overlapped by the undifracted waves through the hologram. To ensure unoverlapping, we need to determine the minimum angle that the reference beam can make with the recording plane. So we need to determine this angle, because this angle will decide how much away the diffracted wavefronts, that is the term containing R star and the term containing O star, will move away from the undifracted beams. The amplitude transmittance of the hologram following equation number 6 can be written as given below. So this is the amplitude transmittance. But you know that now we are writing the amplitude transmittance in another form. So you see that we have the same. The first line is the same as we took from equation number 6. In the next line we have substituted the value of R, but in the form of a phase factor. That is, R star is replaced by R mod multiplied by e to the power plus iota phi r, and O star has been replaced by again we have put the O star as such, but you know that we have replaced the R, that is the reference beam, again by its original value, which is the absolute value of R multiplied by e to the power minus iota phi r. So here we are representing R by its values in the form of a phase, and the rest of the quantities are unchanged. Now we are representing phi r as e to the power minus iota phi r as e to the power minus iota 2 pi fy, and on the other side we are using e to the power plus iota 2 pi fy. Why we are using? Because you know that these are related with the frequency of the fringes, which we have also shown in previously, that we have combined the terms in order to write the terms in the form of cosine factors. And you know that in the cosine we have some fringes. We have the cosine factor produces the fringes, and you know that we have also the factor that is related with the special frequency of the fringes. So in the writing equation number 12, we have used equation number 2 for the reference wave. The spatial frequency at the recording plane is f is equal to sine of theta over lambda. We have also shown this factor before. So this is f that we have introduced in equation number 12. And theta is a fixed angle with the reference beam, which makes with the y-axis or equivalently with the recording plane. Here we are assuming that the recording plane coincides with the xy plane. That is, the recording plane is placed at the xy plane. The collimated reference beam is lying on the yz plane and is tilted downward, making an angle theta with the y-axis. R mod is the amplitude of the plane wave at the recording plane, which we have assumed to be constant. Let's compute the Fourier transform of both sides of equation number 12, which is given below. So we have taken here the Fourier transform of equation number 12, and we have shown the Fourier operator. You see that in red, the Fourier operator is there before every term. The Fourier transform of 1 is actually the delta function. So delta of fx, fy is the Fourier transform of 1. And the rest of the Fourier transform have been shown. For example, the Fourier transform of absolute square of O is actually the autocorrelation between its spectrum values. So capital O autocorrelated with capital O in the first term, because it corresponds to the Fourier transform of the absolute square of the object. And you know that for the second term we have O and the exponential. The Fourier transform O is a capital O, and the Fourier transform of exponent is delta function. There is a convolution sign because these two terms, that is the second term, that is the second term within the parenthesis is multiplying, so there will be a convolution between these two terms, and this is the delta of fx, fy minus y, because we have f minus y. And then you know that in the third term we have similarly we can write that for the third term that we have Fourier transform of O star, which will be represented as O star, and within the bracket we have a minus fx, fy, and the convolution is with the Fourier transform of the exponent function, which is a delta of fx, fy plus y. So we are going to do the convolution in the last step, and then you know that O will be, when convolved with the delta function, the arguments of the capital O will be replaced by the arguments of the delta function, and similarly we have replaced in the last step in the equation number 13, that we have replaced fx and fy in the object O, and in the complex conjugate of the object O by the values, by the arguments of the delta function. So here capital O of fx, fy is actually the Fourier transform of the object O, is the spectrum of the object. It is required that the three spectral terms lying within the parentheses in equation number 13 should be unoverlapped. We have shown the Fourier transform so that we can show the angle between them. You know that this term will be located at the position y, that is capital O. Within the parentheses, look at the term, the third term, which is R mod, and multiplied by capital O, and capital O you know that now exists at the coordinate fx, fy minus y. So fy minus y means that it exists at a value of fy is equal to y. And in the O star you will see that you have the coordinate minus fy is equal to minus fy minus y. It means that it will exist at a coordinate fy is equal to y, and the other term will exist at fy is equal to minus y. So one term will be located, that is the spectrum of that is capital O will be located at the location fy is equal to y, and the O star, which is the complex conjugate of the spectrum, will be located at fy is equal to minus y, as always from equation number 13. So let's assume that the width of the spectrum O is w. Now you see that we are, in order to demonstrate further or to explain further the unoverlapping between them, we are assuming that the spectrum of capital O, the width of the spectrum of capital O is W. Then the width of the autocorrelation term will be 2W. That is this term, which is O autocorrelated with O, that is the first term in this parenthesis in equation number 13. This is the autocorrelation term that will have a width of 2w, and the width of the conjugated spectrum will be w. So the width of this term, that is the first term within the parenthesis, which is the autocorrelation term, will be 2w, and the rest of the two terms, that is capital O and capital O star, will have a width of each will have a width of equal to w. The location and the width of the spectral terms in equation number 13 are shown in the figure shown on the next slide. The spatial frequency f is equal to sin theta over lambda controls the separation between the consecutive spectral terms. So please make one correction over here in equation number 13. That is, it should be fy minus f. This f, you know that we have f over here. This f is the spatial frequency of the fringes. So this f, which is present in the exponent in this equation, so rather than y over here, it should be f. So delta of fx comma fy minus y. And similarly, in the second delta function, we have delta of fx comma fy plus y, fy plus f. So please replace y with f, that is f from this one. So this is not y in equation number 13, but it is f. The same f that would appear over here in this formula, that is f is equal to sin theta over lambda. So please make the correction in equation number 13, that y in equation number 13 should be replaced by f. This f, you know, that which appears in the exponent form, and this f which is given over here, that is f is equal to sin theta over lambda. So the spatial frequency f is equal to sin theta over lambda controls the separation between the consecutive spectral terms. For the spectral terms to be unoverlapped, the following condition must be satisfied. You see that here I have shown correctly that the argument of capital O, we have fy minus y, not fy minus y. So fy minus y is shown and fy plus y is shown on the terms which we have, which on the term which shows the absolute value of capital O and the absolute value of O star. The arguments are respectively fy minus y and fy plus y. So these have been shown on the side terms, because we have shown this plot on the horizontal axis. We have fy which has been shown on the horizontal axis. So this term, which is capital O, will be located at the absolute value of capital O will be located at the location fy is equal to plus y plus f, and the other term, which is absolute value of O star, will be located at fy is equal to minus f. And you know that we have shown f and minus f also from its central position. So we have shown plus f and minus f from the center of this position. That is, we have shown the center of the location of the absolute value of O and the absolute value of O star. And you know that the rest two terms we have shown. The rest two terms is the autocorrelation term between the spectrum, that is O autocorrelated with O, and the other term is a TB term. So we have shown these terms because these are the unaffected terms. We have shown these terms in the center. And the caption is location of spectra and their widths according to the terms given in equation number 13. So you see that we have shown all the four terms. The two terms which are unaffected are shown in the center, and the width of this center, the central width of these terms is 2w. You know that we have shown half of the width, which is w, and the other two terms, which is the O mod term and O star mod term, they have a width of w, half width of w by 2, and the total width is w. Okay, and we want them to be separated. So it means that if f is smaller, then there will be an overlapping between the terms. The central terms remain unchanged because their location is fixed at fy is equal to 0. So this term, that is the two terms we have shown in the center, they are located at f is equal to 0 and fy is equal to 0. So their position is fixed. The position of only will change for the absolute square of the mod of O and the mod of O star, because they depend upon the value of f. So if f is greater, then they will be well separated from the central terms, and if f is smaller, they can overlap the central term. When the reference beam is much stronger in comparison. So let me show one more thing over here. So you see that R mod is present with the term capital O, and R mod is also present with the term O star. So if you make R much stronger, what will happen? The O will be stronger, because you can consider that the amplitude of O is R mod, and the amplitude of O star is also R mod. So if you make the reference beam stronger, it means that O and O star will be stronger. So this term, which is the autocorrelation term, can be rejected in terms of this addition, because if R mod is much stronger, then you can neglect the contribution of O autocorrelated with O, that is O autocorrelated with O. This spectral contribution can be neglected if R mod is much stronger. And you know that this TB is just the focusing of the reference wave. This is just focusing. So this forms just a point source, that is delta of fx comma y is just a point source. So this whole information is gathering at this point. So it means that we can narrow down the central contribution in comparison if R mod is much stronger. That is, if the reference beam is much stronger, then of course the central part can be reduced in width in comparison with the O mod, which is the mod of O and which is the mod of O star. As I have explained using this bracket, that if R mod is much stronger, then you know that the contribution of O autocorrelation of O, capital O, can be neglected in comparison with this one. So the width of this one is 2W. So it means that if this is neglected, the width is reduced, and then we have a precision that we can control the value of f, the frequency of f. So again, this y in equation number 13 should be replaced by f, and f is the special frequency of the fringes. That is, from this one, f is equal to sin theta over lambda. This is f, as I have correctly shown in this figure. When the reference beam is much stronger in comparison with the object beam, the spectral term corresponding to the reference beam also becomes intense in comparison with the term due to the autocorrelation between the object spectra. Physically, only focused reference beam is observable, and the object spectra, that is O, as a function of fx comma fy minus f, again fy minus f, and its conjugate, which is O star at the coordinates minus fx comma minus fy minus f, not y, minus f, can be allowed to come closer to the focused reference beam at delta of fx comma y fy. In this situation, equation number 14 can take the following form. So you see that from this equation it is clear that f should be greater than w plus half w, so that the two terms are just separated from each other. So this is what we have written, that is, f should be greater than w plus half w. And you know that f is the special frequency of the fringes, which is sin theta over lambda, should be greater than equal to 3 by 2 w, because w plus half w is equal to 3 by 2 w. And from here you can find out the value of angle theta, which is equal to, so theta should be greater than equal to sin inverse of 3 by 2 w into lambda, as given by equation number 14. So this provides you the value of the minimum value of angle theta that you can use in order to make the side two terms to be separated from the central term. But you know that if the beam is stronger, as I told you, then this 2w width of the central peak of the central area, which is due to the autocorrelation of the spectrum of the object, that can be reduced to much smaller quantity. or may be neglected. So the two W widths can be neglected. In that case, we can bring this mod of capital O and mod of O star much closer to the coordinate Fy is equal to 0. So it means that then the constraint will be W by 2 only. So we can bring capital O mod close to Fy is equal to 0, so that the separation between them is W by 2. So in that case we can write, so in the case of stronger reference beam, we can say that the special frequency of the fringes should be greater than equal to half W. And then you know that F is equal to sin theta over lambda should be greater than equal to half W, and theta is equal to should be greater than equal to sin inverse of half W lambda. So in case of stronger reference beam, we can reduce the constraints on the angle theta. So you see that in both cases, that is in equation number 13 when we are using moderate value of the reference beam, and the equation number 14 when we are using much stronger reference beam have been given in equation number 14 and 15. The constraints on the angle have been given and have been explained. So this is the end of slide number 71.